of course, this is minus h bar lambda FB, and this guy right here is equal to, sorry, this should be lambda B, and this guy right here should be lambda B squared FB. That is, L squared, or lambda, should be equal to minus h bar lambda B plus lambda B squared. This should be it. And I mean, this looks pretty uncanny, right? The only way this makes any sort of sense is if lambda B is some multiple of h bar. So let's just assume that for a second. What happens? Well, we get lambda is equal to minus n h bar squared plus n squared h bar squared. And now consider that lambda itself, since lambda b is n h bar, lambda itself has to be lambda b plus some amount. Let's call it m h bar, which means it has to be m plus n h bar. So when you have this weight on your shoulders, it means the only possible way through is for n to be an integer and for n squared and n to cancel out with one another. So that's it. N is an integer. What happens? One more piece of evidence backing this up is that since we're getting from the bottom all the way to the top in an integer number of steps, n, that means that this eigenvalue has to be minus n over 2h bar, and this eigenvalue has to be n over 2h bar. And one more thing to reinforce that, you might ask, well, don't we pass over 0, which means everything after that gets crossed off? Well, no, perfectly fine. You can pass from minus 1/2 h bar to 1/2 h bar without ever touching 0. So there we go. We now know what all the eigenvalues are. All the possible eigenvalues are just some integer h bar over 2. So that is the end to part 3. Now it's time for part 4. We know the eigenvalues. Now it's time to find the eigenfunctions. So I want to start this with a callback to what I said. P is basically just I squared nabla. So then, that means P cross R, which is angular momentum, is just IH bar nabla cross R. Now what I'm going to do is convert to spherical coordinates, which sounds like a dumb decision, but we don't have many other choices. So R becomes R the scalar times R hat, the unit vector. Expanding this out gives us IH bar multiplied by, what is nabla in spherical coordinates? Well, we have R hat cross R hat, partial R, plus R hat cross theta hat divided by R, partial theta, plus R hat cross phi hat over R sine theta, partial phi. So this is what we're now working with. So the vector cross itself, we isolate the scalar, it has nothing to do with the cross product, is equal to 0. So this term disappears. R cross theta is phi, and these two disappear. will also disappear. R cross phi is minus theta. Which means that we're left with I bar multiplied by phi hat partial theta minus theta hat cosecant theta partial phi. Now, we're doing pretty good so far. We want to convert all the way back to Cartesian coordinates. Not these guys, obviously, they're too far gone. Just partial theta and partial phi. Why? Because we used to have Lx, Ly, Lz. Those are nice. We don't want to convert to Lr, L theta, phi. Those are probably gross. So instead, we're going to see what we can do if we express Lx, Ly, and Z themselves in terms of Lr, L theta, and L phi. So what if we do? Well, consider spherical coordinates. In spherical coordinates,